It's my pleasure to introduce the chair for the next session, which is Daniel Rivera. He was one of Manfred's early students. I almost made that mistake again. Manfred's early students, he had a career in control-relevant identification, as well as process control more broadly, and then moved into sort of health-related research. And he will introduce the next speakers. And I've known Daniel, 60% of my life, so yeah.
Hopefully the best part.
So,
yeah, well, thank you, Richard. Well, thank you. Well, again, I'm at Arizona State University, and I've been there since 1990. And I guess every chair has said a little about their relationship with George or interaction. Back in the early 80s, when I was considering graduate school, I was at the University of Rochester, and I asked professors, I was interested in controls, and they said, well, consider going to Minnesota to work with George Stephanopoulos, or Wisconsin with Manfred Murari. So when I visited Minnesota, George had already left. And so contrary to Madras, I did not have a choice. But I still was able to remain in the family. And George, your legend grew from stories I would hear from NTU students that you had taught out in Greece. Evangelos Safirio, he'll probably have some stories tomorrow to say. And Kostas Sakalis, who's a colleague at Arizona State. And of course, we interacted over the years. Your son is a professor in chemistry at Arizona State University. And George will actually be spending some time with us. He's actually getting an appointment at ASU. So we're happy to have you as a visitor anytime. Winter visitor, which we call snowbirds. Fall as well, summer. We're happy that you will be having a closer link with us at ASU. Let me introduce our first speaker. And Gabriela Henning is a professor at the Universidad del Litoral in Argentina, in Santa Fe, Argentina, and director of INTEC, Research Institute at that university. She was in George's graduate class on process systems engineering at Bahia Blanca almost 40 years ago, and then they met again in 1986 as she came to do a postdoc here at MIT, along with Horatio Leone. She was a developer of the modeling language Modela, which introduced many new ideas in computer-aided engineering. Okay. And she will be talking about process operations, a roadmap from the present to a hyperconnected future.
Thank you, George, for the kind invitation. It is a great honor to be here. Thank you to MIT also. And it's not almost 40 years. I look old, but not that much. It's almost 34 years. It was a turning point in my life. I went to Bahia Blanca. George had the Greek connection and an Argentinian connection at that time because of friends that he made at Minnesota. Used to go to Argentina, to Bahia Blanca mainly, and then to Santa Fe several times. And a friend of mine invited me to join her to take George's class. And I was amazed by that class. And I was more amazed when at the end of the course, we were having a party at the canteen. George was planning to come to MIT and invited me to join the future group here at MIT. I was finishing my second year of PhD studies, finishing courses. So I said, it's a long way to go, and there is a problem. I am married. The person that was mentioned is my husband that is over there, is the other Modela person. And another problem came next year because I got pregnant. But anyway, almost 3 years later, we came to MIT and spent almost 3 wonderful years working as postdocs. So I'm really happy of being here. And I want to share with you something that George, as a mentor, said to us when we were leaving. I do remember perfectly that moment in his office. We were finishing discussions about what to reply to the reviewers of the Modella paper, and we were just leaving MIT. And at that time he said, guys, you have been very lucky of being here, but now you are going back to your country. You will face difficult times, but you have an educational mission going back to Argentina. And that was very enlightening and was a guidance through all the years. And we took that very seriously. Both of us grew up in our careers, and we are trying to do our best. Okay, now moving on to my presentation that is very difficult to make because a lot of interesting people have talked about. I will talk about PSC, and I had the same feelings that Manfred had this morning, shared this morning. I read some papers, and I read the predictions that researchers have done. And in many cases, we fail miserably. But let's analyze a little bit what we have done in PSC and a little bit of processes, operations evolution, just a part of process operation. So then I will move to the challenges and the opportunities that are opening right now, and then the dangers and opportunities of a hyper-connected future into fields, supply chain management and scheduling. And I will try to give some guidelines to take advantage of the hyper-connected future. Well, PSC, from past to present. Many things that are here have been said during this morning presentations and this afternoon talks. We have moved from steady state and spatially lumped models to dynamic and spatially distributed modeling, simulation, optimization. We have moved from isolated design to systematic methods for tackling process and network synthesis, from large plants to process intensification, from chemical and petrochemical products and processes to pharmaceutical, biotech, systems biology, as well as particulate and nanostructure products, and so on and so forth. And the same I can say about optimization and the formulations that we are using or developing. We had a nice presentation by Larry. Also in the field of control, from simple monitoring and control to model-based control and real-time optimization and things that are beyond. From controlling and managing just a simple process plan in isolation towards the agile management of process plan in the context of a supply chain where several actors interplay. And I can continue, and I will, it's just some few points. We have made an improvement. We have made our way. In the field that I will be talking, we have moved from production planning and scheduling to enterprise-wide management to supply chain management. And from the analysis and optimization of simple systems to horizontal and vertical integration of systems that need to be optimized. From taking care of just economic objectives to take care of a lot of issues, environmental, sustainability, energy, etc. Okay, so using some of Wolfgang Marquardt's ideas. It's like we moved from PSE from selected unit operations and simple processes to the enterprise, and we are now in the era of multi-enterprises. And as I mentioned, that opens up a lot of challenges and opportunities. When I chose process operations, then I said, too ambitious, too ambitious. I will not talk about the whole field, but let's look at the evolution of the field. The first FOCAP-O conference was in 1987. Looking at the proceedings, I took the one of 1999, for example, that was representative of this period, and we saw some regular, usual topics: planning, schedule, identification, control, dynamics, diagnosis, and some emerging or new hot topics: plant-wide optimization, environmental issues. Only just three papers about supply chain management. That was not supply chain management in the concepts that we see today. Let's move to another period, the period that we are now finishing. The old issues, the old regular topics are sitting over there. We are still continuing working on them. But we have new topics: supply chain, integration, stochastic optimization, sustainable resource management. And the question comes about the next 2 decades. What is going to come up there? I don't know. But what we know is the kind of world we are living right nowadays, and the opportunities that are open now because of great technology advantages that we can use. Well, we are in a globalized competitive economy, so we have volatile markets, an uncertain demand, sharp fluctuations in fuel pricing, and so on and so forth. We face tough customer service requirements. It was mentioned this morning, dedicated products, more sophisticated products, coupled with a lot of requirements about services attached to those products, accurate deliveries, high levels of efficiency, etc. These products that, of course, are products that are having shorter and shorter life cycles that end and are replaced by new products. So we have increasing levels of product varieties, and that increases the uncertainty of our predictions of our markets. Those are things that are pushing us to be more efficient, to put constraints. But on the other hand, we have opportunities. We are in the middle of a big change in the technology opportunities that we have. We have a proliferation of mobile devices, pervasive connectivity, a lot of sensors that appear everywhere, more computer power, much more computer power that was mentioned in previous talks, the Internet of Things, the industrial Internet of Things, the Internet of everything, as some people mentioned, big data, cloud computing. So we are in the middle of a set of technologies that we have to take advantage of. Some people say that we are in the middle of the fourth industrial revolution with Industry 4.0, smart manufacturing. We are in the middle of a changing technology environment. I took this picture from an article from Fujitsu Science and Technology Journal about the ICT megatrends. And they are talking in this article about the impact of big data, cloud infrastructure, and the Internet of Things, and how these mega trends can shape our future. So I will not go into all of them because we will not have the time, but just touch upon some of them. This fourth industrial revolution is based on the comprehensive use of cyber-physical systems. The aim is to extend the impact, the digital impact of the third industrial revolution that was based on automation, mainly based on automation, and makes available a huge pool of technologies, new technologies, and information. From the point of view of process operations and from my perspective, this set of technologies makes much more broader the scope of process operations. It continuously expands the system boundaries. We put boundaries, and those boundaries are expanded. And this, of course, introduces challenges, threats, pressures, of course, opportunities on the other side. I will concentrate on this, but just for the lack of time and for the lack of knowledge, these are the two topics on which I will feel more comfortable to talk about. Let's speak about supply chain management. As I mentioned, in 1998, at the FOCAP-O meeting, just 3 papers, 2 papers and 1 plenary lecture, and very limited scope of supply chain. At that time, it was mainly known as logistics, and the support systems that were in industry were ERP systems. In most of the cases were not the commercial ones, but some in-house developed ERP systems. Supply chain was procurement and distribution, and just how to do good procurement, good sourcing to factories, and how to reach customers in an effective way. So it was MRP, materials requirement planning, and DRP, distribution requirements planning. Some chemists didn't know those ways of solving problems because those became from other fields like industrial engineering. Unfortunately, very quick, we realized the importance of the supply chain. And in these 2 decades that we are now, the supply chain for us has an increased number of partners, several echelons in a different sense that it was mentioned this morning, but still has a company-centric view and a linear alignment of echelons. The informatic applications that are used on a daily basis are supply chain management systems. Of course, the situation is much better than 20 years ago, but still is not the best situation. Because what comes is a new type of supply chain, a nonlinear, multi-enterprise supply chain. And as it was mentioned in previous presentations, the supply chain has customer centricity. Special products dedicated to customers, special services requested by customers that want consolidated visibility that is a requirement for all the partners that are comprising the supply chain. This is the current status. Nowadays, we are on the process of going towards those supply chains, and we face weaknesses and threats. Supply chains are changing a lot, and we come up with solutions, for example, to configure, to make the synthesis of a supply chain what we call strategic solutions. And those solutions are decoupled from the tactical and the operational ones in most of the cases. The integration is very limited, the integration among the partners, and the interoperability is very rich. There is an absence, very limited collaboration between business partners, unfortunately. And there is a lack of holistic end-to-end visibility of the data. This end-to-end visibility is the enabling matter to do a holistic decision-making type of process. In many cases, we still have unsuitable data handling. We either lack data or we have a jungle of data with minimum informative value. And of course, because we are in the middle of a changing environment, as I mentioned, this is constantly changing, what we are facing is an increased level of uncertainty. So we have a supply chain that is not very strong. It has some weak links, weak echelons. So how are the 2020-2040 supply chains going to be? Well, ubiquitous data and enhanced visibility should be present. Increased asset virtualization for every single physical asset. There will be a virtual copy in some cloud. Hopefully, we will have a knowledge-enabled workforce. People, the millennials will be fully working, will be the workforce, and they will be involved in the management of the supply chain. The links among the partners that are dynamic nowadays will be more dynamics. Supply chains and their associated business processes will be constantly morphing, transforming themselves because of the type of products, their short life cycles, and that will come up with shorter time frames of strategic and tactical decisions. So the hierarchy of the supply chain will be flatter. It will flatten, and the levels, the boundaries between the levels will blur. So this poses a requirement, a capacity to develop supply chain management systems characterized for self-adaptive dynamic models able to cope with the modifications, continuous modifications of the environment, and to empower the human involvement. Let's move to the other field I would like to talk about. I would like to talk a little bit about scheduling. The first 2 decades that I am characterizing here can be seen as, well, the first steps towards more elaborated solutions that we have nowadays. We were, at that time, we were focusing on low dimensionality problems. I will not give numbers as previous speakers, but I can tell you that to solve a problem with 12, 20 orders in the early 90s, I was leaving the problem to run and going back to Intech at midnight to see what happened to that. And this is a toy problem that we give to undergrads. The solution methods were very simple, mainly heuristic, dispatching based on dispatching rules. And we had the first MILP-based formulation and the first STN and RTM-based methods. Now, we have more systematic approaches, more elaborated time representations. There are wonderful papers about the different ways of representing time, the more effective ones. We have formulations that can take into account limitations on resources, something that we didn't have over here. We have started to take into account uncertainty in a more effective way. And there are some attempts to integrate scheduling with control and planning, but we haven't been quite successful up to now. Delay. What will come up? Well, hopefully in the next 2 decades, we will have comprehensive scheduling approaches. Comprehensive in the sense that we will integrate predictive with reactive, and we will also encompass the consideration of uncertainty. We will have integration of scheduling applications within the enterprise and supply chain software, and hopefully more comprehensive uncertainty handling. So hopefully we will manage our supply chain and the impact of our scheduling within the supply chain. So we will have a picture like this: the supply chain, the production plan, scheduling, and a lot of data that is available to make correct and knowledgeable decisions. But this is the idea to reach. Where are we standing right now? Unfortunately, and since 2009, that I wanted to be provocative at a PSC meeting, things haven't, from my point of view, changed too much, and our academic developments have not penetrated the industrial practice to the extent possible. One of the reasons, there are several reasons, one of the reasons is the lack of high-level languages for model development. We cannot ask industrial practitioners to master our MILP and MINLP models. We should go for tailor-made model development if we want to get a penetration into industry. Another issue that is important from my point of view is that our solutions approaches are neglecting the human interaction. And this is something that has to change. And of course, the lack of integration of the scheduling function within the enterprise and supply chain dimensions, the decoupling of the different type of solutions, the predictive and the reactive, not integrated at all, and still a weak treatment of uncertainty and disruptive events, which are becoming increasingly important. So, in this last part of the talk, I would like to point out some issues that I think we should work on if we want to take advantage of this bunch of technologies, this hyper-connected future. So the questions are how to master the digital innovation challenge, how to take advantage of it, how to take advantage of a hyper-connected environment. And here I have pointed out some issues. I will not develop all of them. Fortunately, we have nice presentations before, and probably we will have more nice presentations on some of these issues later or tomorrow. One of the points is the comprehensive big data handling capabilities. Simply collecting data and making it available to a wide audience does not guarantee anything. On the contrary, it might lead to chaos. So the question is how to structure data. There are a lot of people working on that field from the computer science, and some people working in our field in PSC in big data methods. But I think that we all should know, if we want to take advantage of this technology, know a little bit more. At the FOCAP meeting early this year, I've seen some papers that they were just using the technology, but without the proper knowledge that should be behind it. The idea is how to articulate huge amount of data that have different syntaxes and semantics of several partners. Probably in a supply chain, we will have providers, the customers, logistics providers that represent things in different ways. And the data will come from all of them, and those data should be merged and something meaningful should be extracted. So my point would be to develop big data management frameworks that are integrated with the process operation applications. Something that I have seen is that we take the data and we extract some conclusions, we do some predictions, but those things are not integrated into the whole framework of process operation applications. So we have to incorporate competencies on big data analytics, descriptive, diagnostic, predictive, and prescriptive. What happened, why it happened, what will happen, and what actions to promote, but not in isolation from the rest of the process operation functions. Just integrated with them, regarding big data applications, it is, if we want to come up with integrated solutions, we have to understand the data, garner information and knowledge from data, and intelligently combine data from different sources. But here comes a problem. We need to be able to represent the assumptions, the conceptualizations that underpin knowledge in the application domains. And data creators and publishers need to make explicit what the data represents together with the context of the data and its creation. So this is some field we have been working with Horatio in the past years, and currently is the development of domain ontologies and ontologies for the big systems. For the big systems we haven't started, but it's an idea that we have. Ontologies and ontological analysis are vital part of any solution that are addressing problems of architecting and engineering big or complex systems. From our point of view, ontologies can be used to make explicit and accessible the critical assumptions about the nature and structure of engineering systems and their components. They can help people to understand and disentangle the complexity of big engineering systems and their environments, being it social, economic, or whatever, and enable the integration among systems and data through semantic interoperability. Speaking about integration and collaboration, this is something that we mention continuously, and sometimes we don't understand quite well. Integration is not just data exchange. It should be based on semantic interoperability. Another issue, if we are thinking of a more collaborative world with many partners, integration is a team task. For example, let's think about the development of a supply chain performance evaluation system. We want to evaluate the performance not of the supply chain of a company, but to articulate all the partners that are involved, including, for example, the logistics providers. Well, of course, it should be a team task. Through integration, is based on synchronization and collaboration of business processes. Nowadays, it should be seen as a model-based problem, not data-based problem. And true integration would allow developing a genuine multi-scale behavior. I will not talk more about this issue because several presenters gave wonderful ideas, but in order to manage multi-scale behavior, we have to manage different models at different scales, and we have to integrate them, and we need to have a meaningful representation. So speaking about integration and collaboration, and just to give you a simple idea, interoperability is about communication and information exchange. We would like to go towards collaboration, having common business models that are based on ontologies and reference models. Collaboration is a demanding process in which participating entities share information to jointly plan, implement, and evaluate a program of activities. Another point I would like to make is about knowledge-enabled workforce. We want to move users of our systems to the self-training paradigm that millennials are used to. It is not the paradigm that we have, but it's a paradigm to look for. And something that we would like to have is decision support systems in which humans can interact with the application in the same way they interact with other humans. So we need to systematically integrate humans into the problem definition and solution process, but without requiring them expertise. For example, something that has not been developed, but is something to look at, is the mixed initiative of optimization systems that look at complex optimization problems as complex socio-technical systems, and they look at the complementary capabilities of humans and computational systems. So the idea is to empower the user and to bring him or her as a part of the solution of complex problems. Another issue that is necessary to take advantage of this hyper-connected future is a comprehensive treatment of uncertainty. I will not develop that point. Fortunately, we have Matthew, and we will have other presenters. It's not, I am start working on some uncertainty issues in scheduling, but what I'm sure, I'm not knowledgeable in the field, but I'm pretty sure that we need a comprehensive treatment of this field to characterize and quantify uncertainty. And that Matthew pointed out that is very important to feed up our models with the characterization and quantifications of parameters that we have done. And to end up, something that was also mentioned this morning is that we have to look at modern computer science education quite seriously. Computer science support of process operation goes beyond the development of efficient models and powerful algorithms. I'm not saying that they are not important. They are necessary and they will always be necessary, but they are not sufficient. The solution of complex model will remain, is one of the major concerns and areas of activities of PSE, and it will continue. The size of models will steadily grow up, as well as the number of interactions with other components. That will not change. We have seen a lot of this. But as Kostas mentioned, in order to make these models and these solutions and these algorithms accessible by industry and not just by academia, what we have to look is at other fields of computer science. Kostas was talking about model-based engineering. I would say that along the same lines, we have to master basic software engineering principles. We have to know how to develop pieces of software. Computer science people know how to do it. We should know it. We should know how to make the elicitation of functional and non-functional requirements and to embrace them in our developments. Validation, verification, things that were mentioned this morning are very, very important. So not only the design of very efficient, good algorithms, but the comprehensive development of systems from the early requirements towards the validation, the verification, the implementation, and the maintenance, something that many times is missing. We have to learn and develop new computer science methodologies and technologies, ontologies, big data handling, cloud computing, machine learning, and the like, with the experts in the fields, which are computer scientists. We can learn ourselves, but we have to interact with these people that know better than us about the field. And with that, I would like to thank you for your kind attention. I would like, again, George, for the opportunity to say that I'm really happy of being here.
Do we have one quick question for Gabriela? Okay, well, let's go ahead and thank you again. Okay, so our next speaker is Eric Yitzhak, who's professor of chemical engineering at Carnegie Mellon. And Eric and George have overlapping interests in process control, have known each other for a long time. And they have one thing in common, in that they are both individuals coming from the academic community who have been research directors, have had management posts in industry. Eric took a leave of absence from Carnegie Mellon to assume the position of R&D director at Elkem ASA, and is also involved with Solar Silicon LLC. This is around the same time that George was at Mitsubishi Chemicals. He has degrees from Imperial College. He was at the University of Massachusetts for 10 years, and since 1992 has been at Carnegie Mellon. And the topic of his talk is distributed decisions and the adaptive enterprise.
Thank you so much for asking me to come here, George. It really means a lot. I'm among many people I know well here, and you know me, so you know roughly what to expect. I'm going to, instead of talking about something I understand, I'm going to talk about something I don't feel I understand very well. And so we're going to start out. So we already heard about the history in terms of the 4 industrial revolutions, the steam engine, the mass production, the industrial revolution uses electronics, IT, etc. And then the 4th industrial revolution, which is the first one that actually was announced before it arrived. So that's where we are. So some of these slides are from actually FIPSA 2 in Crete. I promised Christos to write the paper based on this, so now we're going to actually put it together and get it out there. But so I have to acknowledge Alfie Saxon of IABB and Riccardo Scatolini from Politecnico di Milano. So with that much as an introduction, okay, so let me see. Yeah, so let me talk, we've talked about this a lot, so let me very briefly talk about what we call cyber physical systems. So we have algorithms that we talked about that's advanced very, very quickly. That's a service system, if you want to look about it that way. We got data storage, and then at the bottom we got the physical objects. Now, what I want to do, what my interests really in the last few decades in research have really been the physical system, and trying to ask the question from the point of view of process control. What is control and what is the process we're trying to control? I feel these two objects needs to be defined properly in order to move ahead. Now, what I really wanted to talk about today, but George decided that that would not sit so well with this audience, was the stability of the multi-component flash. And it's still a problem I haven't quite worked out completely, but that we decided to talk about this instead. So here we are. So some of you have seen these slides before. This goes back to the famous pyramid that we've been working with from a control point of view, where we have got the PLC, the programmer logic controllers, on-off controllers, or supervisory controls at the bottom. We got the regulatory control, the PID controller, the model predictive control, real-time optimization, planning and scheduling, and then a fairly thin connection up to the dollar sign, as you see at the top here, focusing more on stability and robustness. So that was the pyramid with the dynamic information that flows up. Now, we had the parallel development in FOCAP-O, which is the operations community, and they have what I call the inverted pyramid, which does not focus on stability at all, but rather focus on the big dollar sign and have the decisions flow down under the authority of the optimizer. Really, I think what is remarkable about George's career and his program that he set up was really that he merged these two pyramids together. And right from the beginning, with these important papers back, Manfred Jan Monarkun and others from University of Minnesota, a sequence of 5 papers, I think it was, really laid the groundwork for an understanding that all of these problems hang together, and we can't sort of think about them as two separate problems. They have to be merged together. And I think that was a huge contribution, and something that really, I think, has been a leading thought for the whole community. And we get better at this. It's a hugely complicated problem. The aim, of course, is to move towards optimal decisions. I think the control people, in some sense, were more interested in formulating tractable optimal control problems, whereas the optimization community was more interested in how do we actually solve problems. And now these things come together. I have the good fortune of being in a department where I've got a number of colleagues who are great experts in optimization, and I must say I've benefited enormously for being a part of Carnegie Mellon and that effort there. I do understand and respect what numerical optimization can do and the enormous advances that have been made in that field. So PSE challenges and applications. So I think when you talk about cyber physical system, Gabriela brought this in very, very succinctly, I think, and Kevin Joback, I really enjoyed your presentation too, this idea that we're looking at fairly flat systems, maybe many systems that are interacting together. So that's a little different from these hierarchies that we've been working for. These are embedded systems with components that change, very flexible, very fluid, changing markets, changing algorithms, changing hardware, changing software, all of this all the time. And I don't think our systems are really set up very well to deal with that challenge yet. I still think, and again, this back to Gabriela's talk, there's been huge advances made in computer science, especially in the area of logic systems that can benefit our community quite a bit, evaluating essentially in real time very, very large systems. So, of course, these are NP-complete, NP-hard problems, but still, 10 years ago, algorithms, hardware, were not really up to the task of doing anything of that sort in real time. Now we can solve a reasonable problem in a reasonable amount of time. Lots of big data. So I'm going to talk a little bit about data next. time series, audio, video, but how much information is there really in that data? Matt talked about that in his presentation. We can have big data, enormous amounts of data, but the information contents might be very weak. So the question then comes up, how do we integrate models, algorithms, sensor, physical devices, and adapt these networks, if you will, in real time? That's the problem that I don't know how to solve, and I don't feel I understand it very well, but I'm just going to talk about a little bit how I understand it at this point in time. So the problem of big data is not new. This goes back to essentially Tycho Brahe finished a program where he amassed enormous amount of data to describe the planetary motions. And at that point in time, the program supported by the Catholic Church really was to try to match this data by using transfer function, a Fourier series, if you will. You cannot argue with the accuracy of this. Applied to our solar systems, there's no doubt that you could make very, very accurate predictions as far as you please with that model. So it's not a question of accuracy, but it is a question of parsimony. So let me sort of, just as a background, put up, I'm not going to go through this flow sheet at all. It's an industrial process that we worked with, an oxo-alcohol process. And when you go through this, gets responses, this was what they presented us with, was the reactor feed rates were oscillating like you see on the left here. In fact, every single variable in this plant were oscillating and had been oscillating for 20 years. They produced and they were doing fine, but it didn't really make much sense for them to do much optimization, steady state optimization on top of this, which is what I wanted to do because the plant was not operating at steady state. Now, it is intriguing if we plot out on the right here, you can see this is a plot of the abundance of lynx and snowshoe here. They measured the number of pelts that the hunters were bringing into the Hudson Bay Company. You can see in terms of just looking at this, you can see in data matching, it doesn't really matter whether you're mapping lynx or here, or whether you're mapping out the oscillations in the chemical plant. But it should matter. I mean, somehow, I think we need to make sure that we're not controlling the Hudson Bay Company, but we're actually controlling this oxo-alcohol plant. It's also another thing is, and I think a weakness of the data-centric point of view is that you can amass an enormous amount of data in ExxonMobil trying to translate any of that to Dow Chemicals, and you'll fall up short. You have to do the same exercise again. So I'm not necessarily criticizing the technique. I'm just showing some thoughts out there that I haven't worked out. So, of course, the physics came to help in the form of Newton and later Hamilton with the principle of minimum or least action. That was a very parsimonious way of looking at modeling this system. In terms of predictions, it was equally accurate, but the models are more pleasing. So in terms of optimization control, that should be a better way of going in this. But of course, when we apply it to our systems, the principle of least action, which works so wonderfully well for mechanical systems, is not really well clarified in chemical systems. And that's sort of the thing that has intrigued me a lot in my research. So, but we do have minimization principles, and we have worked on them. There's one on the left that I'll talk about a little bit. I'll talk about the one in the middle first. So this is the V formation of geese. So it's something that we've all seen and find very intriguing. Clearly what's going on here is that the geese, they're batting their wings and flying in a V formation in a sense to minimize the drag. It actually increases the drag a little bit on the leading goose here, but the ones in the back, they yell all the time, quack, 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 like that, to lead on the leading geese until he or she gets tired, and then that falls back and another one goes up. So there's some coordination. It's actually, there's more to it. You can notice it in this drawing here, that they're beating out of phase. That's another condition for optimality in this system. So they don't do, if you watch a video, you can go on YouTube and watch this yourself, you'll see that they're trying to beat a little bit out of phase. And another thing is they don't learn this from the elder geese. This is, these all have they're from the same, they were chicks at the same time, and they're flying at the same time, and they're learning how to do this on the fly, so to speak. It's a self-organizing system, and a remarkably complex one as that. So you can see where I'm going. What I'm thinking is chemical plants, algorithms, everything we're dealing with here as embedded systems. You take a distillation column out of your chemical plant, your optimization algorithm should still work. You shouldn't have to go back and recode it just because you get the more efficient distillation column or get the membrane process or something like that. Everything should flow fluidly together. I'm sure this is something that the PSE company is thinking about very much from a modeling point of view. But I think there's some formal mathematics behind this that are interesting to work. So the people sort of in physics that I've been studying who worked on this goes back to Maxwell, of course, theorem of minimum heat that I'm going to talk about, Harry Nyquist with the fluctuation dissipation theorem. When we think about the Nyquist theorem, we think about stability and robustness. When thermodynamicists think about Harry Nyquist, he's equally famous in thermodynamics for working out the fluctuation dissipation theorem that has led to several Nobel Prizes later on. And then, of course, Ilya Prigozhin, who's got a little bit of a mixed reputation, but he also got the Nobel Prize for the principle of minimum entropy production. So what's this minimum heat theorem of Maxwell? You string out resistors or pipe flow network arbitrarily complex, and you impose a pressure gradient or a voltage gradient on the network, and the network, the current will distribute itself immediately so that it minimizes the heat being produced in the system. In other words, if you've got linear resistors, an arbitrarily large network, millions, 10 million, an infinite number of resistors, will solve a QP for you. And it does it distributed, so it's distributed optimization. You can change the resistors, make them nonlinear. You solve a nonlinear program to a local minimum. You can make them discrete. You can solve LP, or you can have a mix of on-off resistors, solve integer programs. And it will do this automatically distributed. It's not going to be very, we've done this. It's not very efficient, obviously, to set it up in Simulink and solve QPs this way. So in terms of actually solving practical problems, I would say go to Larry immediately, or Nick or Ignacio, depending on what kind of problem you deal with. But the point I'm trying to make here is that nature automatically will solve optimization problems. We're imposing another kind of optimization problem on top, and we end up at some kind of Nash equilibrium, which matches the two optimization problems. And that's the structure that I'd like to understand here. So if we go to networks, it turns out that this, and this is where we spent quite a bit of work and time thinking about. There's Bernard Tellegen, who worked this out for us. The Tellegen or Herman Weyl worked it out before him. It basically looks at the network. We can take our conservation laws, which you see. Is this going back? Yep. So this is the rate of accumulation. Could be momentum, charge, energy, whatever this is the rate of chemical reaction. These are the flows in and out of your reactor if you have like this, and you've got the network of reactors, distillation columns, and whatnot. Then you have, so that's basically the conservation laws, which corresponds to the Kirchhoff current law. And then you've got the voltage law here that basically says that if you add up temperature differences around the loop, you should end back at the same temperature you started out with. So that's the voltage law. So Tellegen then worked it out that for a network, arbitrary complexity, one can group it into a reaction term, a diffusion term, which is called the Rayleigh-Onsager dissipation, and then feedback, feed-forward controls, essentially how you set your boundary conditions in your network. And this formulation here goes back to Brayton Moser. Dessauer looked at this. So those of you control people will see that we've had control people thinking about these problems for a long time. Oster, Patterson, Brockett, thought about this at numerous occasions, and Jan Willems and Jan van der Schaft. And so they all lead into kind of Prigozhin, Maxwell-Nyquist theorems. So the question then, which I asked, I should say, a brilliant PhD student of mine, Michael Wortman, who finished in 2010. I asked him the simple question, his PhD should be, what is the objective function being optimized of a physical system? It turned out to have a complex answer, but we could do it for simple systems. And basically, the idea was to try to see if you do a dynamical simulation of a system, writing down constitutive equations, everything that you have for the system, what is the equivalent dynamic optimization problem being solved? If we understand what that optimization problem is, we could then maybe tweak it in a way that the optimization objective is more similar to something we would like to optimize rather than nature. Nature often wants to do things that we don't want to do. We want to coach nature to do something that's more interesting to us by changing the boundary conditions in the system. So that was the basic idea. And he worked out the answer. And it turns out that for a sort of linear quadratic problem, again back to the two resistor problems, we actually solved two problems at the same time, as we might expect. One is a load balancing problem. We essentially maximize the flow through the system, and the other would be considered the dual problems, where we minimize the gradients in the system. So that is that would be the formulation, and then putting the two together, we get Prigozhin's theorem of minimum entropy production, which works at steady state. Michael was able to work out the dynamic equivalent, so we don't just optimize at steady state, but we actually minimize the long dynamic trajectories here. So these are very, very strong results. I don't claim any practical use of this whatsoever. But it's interesting to me that one can do this thing. Now, there are some parallels, and this was the idea that I wanted to explore a little bit in this talk. But I decided not to do too much of that. I decided instead to spend a little bit more time on the introduction, if you want to think about it that way. But if you got the free market, what I've been talking about is that you got two suppliers between a resource and a product, and you're in a competitive situation. Supplier A and supplier B makes the same product and have the same access to resources. The market will choose the cheaper one. So that's equivalent to the resistive flow problem if it will be solved as a QP, or as in this case, because you choose one supplier rather than the other. If you got the infinite capacity, you'll always choose the cheaper one, and the other one goes out of business pretty quickly. So that's the idea. If you got a supplier, and this is back to something that Ka talked about, this is a less advantageous situation for A. And this is the business-to-business situation that he said was less interesting, whereas this is the business-to-customer, the B2C situation, which was more interesting because they can control the price here a little bit. Of course, we have to emphasize that this is free market. The way to play this game is price fixing, which is ruled illegal in this country, but that's the only way around it, is actually to go in and A and B, they can fix their prices. They're kind of sharing the profit, so it's less serious in that case. So if in this case, it's advantageous that they do not share information. In this situation here, they really, they have to agree that, well, we're going to keep the price at the high level and do the price fixing. So that's sort of the cartel solution to work your way around these optimization problems. So I think you can read this for yourself, but I think the challenge that I see, well, I'm not saying that anybody should necessarily go out and work on these problems, but these are the ones that I lose sleep over, is in the area of embedded systems. I'm thinking that we have a virtual activity, I call it, which is our models, our regression analysis, our optimization algorithm, all of this that's running these predictions. But we shouldn't lose sight of the fact that there's a real activity going on below that we're trying to match. And what I'm trying to understand is what is the structure of this real activity? How is that modeled in terms of the laws of thermodynamics, let's say, in terms of just some very general principles? How do these systems behave? And so I think I wanted to have another 2 minutes. Yeah. Yeah, okay. Yeah, so I thought to respect the audience, I should show an application. So this is an application that I'm working with Peter Adams, who's a student of Seinfeld. And we're interested in taking satellite data that is coming in, terabytes of this all the time as the satellite goes in polar orbits and sweeps around the Earth. So the Earth rotates around it 24 hours and we get data in. And so what we're interested in is to come up with observers that can match essentially terabytes of data with this very complex GeoSchem model that's developed here at Harvard. So these are 3D models, box models, if you will, of the atmosphere, including the atmospherics. So we got input from meteorology, everything. So these are big model system. And then the Thomas part is what was developed by Peter Adams at Seinfeld. So these are population balance models. So so there are 200 chemical species and some 60, 70 size distributions in the model here. And these are a few kilometers in width and height, these boxes. So the way we set it up using these passivity-based observers that really match in with the physics of the system very carefully. So we spent a lot of time developing these observers. But they're distributed, so they can plug and play. You can put them in anywhere and as many as you like, and they don't really increase the computational complexity that much. And what we looked at is what's called the Southern Arctic Ocean Band, just to get this place to start. So we're trying to estimate the rate of creation of sodium chloride particles that then lead to cloud formation just in this band here. So there's no interaction with human activities. So that's a nice, clean problem to start out with. And what we show is that the model predictions are way off in terms of the frequency contents and also the behavior summer to winter. But when we match it in with the satellite data, we can match in with some, it's called a Jägel correction, which was done from a boat that measured salt concentrations out there. So the next step now is to get up to actually look at some soot formation and cloud formation up in Europe, where they have many more measurements than in the United States. And it doesn't look like we're going to get a lot more measurements in the United States the next 2 or 3 years or so. We'll see. I'm not too worried, actually. I think stopping climate change, I think that boat is sort of on the verge of leaving in the minds of most people. So Trump may slow it down just a little bit, but we'll see. I'm hopeful. So there we are. That was the end of the talk. George, I left in one slide at the end. Well, I just skipped through this because these are just as an illustration of how things have advanced. This is these are some 5,000 lines of assembly code that I wrote while I was in Czechoslovakia on an Intel computer that couldn't even do floating point multiplication. So I had to write routines to do floating point multiplication and taking square roots. And it was a little adaptive MPC that actually ran in industry for 20 years afterwards. An early application, 1983 of this. But can do that in 15 lines of MATLAB code. I don't think the Industry 4.0, the new industrial revolution, has to do with reducing that to half a line of code. I think it has to do with something completely different that we don't know at this point in time. But I think it behooves us well to really follow what's going on. And really, as this program initiated by George, Sargent, Westerberg, the Princeton School, Minnesota and others with the modeling, the optimization, all of that, bringing it together. I think we're really getting a good handle on it, and we don't really quite see what is coming next. And I think some younger people than myself will sort of figure out the seminal paper that's everybody's going to refer to 20 years from now. I don't know what it's going to be. So thank you very much again, George. I wish you all the best for your retirement with your family. And I think on behalf of my colleagues, I can extend a similar invitation to what Dan did. So thank you very much.
And we come to our last presentation for today, which will be given by Professor Stratos Pistikopoulos, who's a Thies Distinguished Research Professor and co-director at the Texas A&M Energy Institute. Stratos got his PhD at Carnegie Mellon, and I guess he spent a little bit of time at Shell, and then went to Imperial College, where he joined in 1991 and was there till 2015. And he had a 7-year stint as director of that center. And Stratos and George got to know each other pretty well during that Imperial College time, as George was part of the advisory board for the center. So let's welcome Stratos.
Thank you. It's a great honor to be here to begin with. And first of all, I'm the one who separates you from a very important event. It's a discrete event, but it's a continuous time. So the dinner and gala, so I will do my best not to miss to delay even more, perhaps what, one of the real things we are looking forward. Okay, so the other thing I would like to say is that actually George, from a Sargent's tree perspective, he is literally my academic cousin, a much younger academic cousin, I must say, but that's what it is. Okay, so, and I would like to talk a little bit about a subject that is in the area of real-time decision-making under uncertainty, and I have a subtitle, whether it's an adventure in big data analytics, and we heard a lot about this, or an opportunity. I changed the word mathematical programming to be a little bit more specific to model-based optimization, so to reflect a little bit more. But before I do this, I just want to first reflect on the huge impact that Professor George Stephanopoulos has had on me personally and in my career, and then talk about the problem itself. So let me first, so you would see that my title paraphrased one of the classical references in the open literature when it comes to process systems engineering, and the paper that has influenced my thinking a great deal. So I would like to acknowledge the huge impact that that paper had in process systems engineering, and me personally. We have seen a lot of this. Just want to show that the process synthesis contribution that many speakers prior to me alluded to, the very important from optimization and global optimization in particular perspective that George and Arnold Westerberg pioneer and has been influencing and shaping the process systems engineering community when it comes to this type of problems. And of course, the control perspective that has been elaborated and discussed a great deal here. On a more personal note, George has been a great friend of Imperial College, being on our steering committee and so forth. And one thing that I would like to share with you is, he acted as an external PhD advisor for one of my former PhD students, a lady, Dr. Katerina Papalexandri, on a thesis entitled Flexibility and Controllability in the Synthesis of Mass Heat Integrated Processes. So it was a potpourri of many acronyms, and George offered me encouragement, support, and very valuable advice, who has, in fact, had a great impact for me for life. So let me share this for you. First of all, he encouraged me a lot to work in the areas of process synthesis, which, he pioneered. Process intensification, because that mass heat transfer modular representation that we were developing at the time has now actually become more fashionable and very fashionable in the context of process intensification. interactions of design and control, which was a theme that he has pioneered, and a lot of the school of thought also at Imperial College at the time, we took that to have decision-making and uncertainty. Some of the problems I'm going to talk about later on today have been impacted by George. But the most important, valuable advice, which has been an advice for life, is that he taught us in many ways, and he personally shared with me the importance of that the key in research is asking the right type of questions. And he advised also a very, very valuable advice that I found at the time was that he shared with me that, and just to have one area where you publish regularly so that you become, let's say, well-known, and have a more risky area that might have much longer-term impact. But the key that I would like to show in the presentation, what I'm going to show you is some recent thoughts, thinking about the decision-making and uncertainty, is the strategy and philosophy is critical to the research innovation. So the message is first get the big picture right, so move from the why to how to what, not vice versa. Because very often we're all preoccupied, we're looking into the details in our little algorithmic developments here and there and forget why we are dealing with all this. So let me move then and share with you some thoughts really for the future on decision-making and uncertainty as we move towards 2040. Okay, and some obvious question is how far we have advanced in other areas between, let's say, 98 and 2017, and then make a projection all the way to 2040. So computing power has been elaborated a lot, has increased by almost 1 billion times. Simulation, and I didn't pick one of the PSC limited for avoiding conflict of interest, but from other type of works, you can see that simulation has also advanced by at least 1 million times in terms of problem size. And we have heard earlier, the wonderful advances in optimization for mixed and linear, for continuous optimization, dynamic optimization, and so forth. And there are similar trends in data analytics. And it's also interesting to see now what is the, we did a little bit of, a funny check, like in terms of trends in word usage, and there are now tools that you can do this. And here I just show you, for instance, the frequency of things like simulation of words, optimization, stochastic data analytics. So just to appreciate the trends. And if you look also in more in the context of the presentation in terms of uncertainty quantification, the blue line, decision-making, the uncertainty, robust optimization, stochastic programming, all these trends, you see the blue line, there is a upward link, and obviously there is an even bigger upward links if you project into the future for big data analytics and so forth. All right, so the key question that I asked myself, and I just really wanted to address in this type of audience, and I was provoked by the futuristic invitation by George, is this so in the context of decision-making under uncertainty, as we move forward, is this an adventure in big data analytics? Is it an opportunity for model-based optimization, or what? And we heard today, we are in the modeling business, and there are models and supermodels, as I say, but we also talked about model-free environments. We are all we always work very well with equations and so forth, but we also talk about equation-free. We are very comfortable with variables, but we also talk about variable-free environments. Derivatives, we all love derivatives, but we love to hate them as well, and we talk about derivative-free environments as well. So I asked the question, is that so? All this kind of free type of environments is the way forward in the context of decision-making under uncertainty? Are there myths and misconceptions? What is perception and what is reality? And I'm not going to answer all these questions. It's more like a thought-provoking kind of lecture, okay? And if we look a little bit more carefully, the type of questions we would like to answer is, can we really innovate, propose new kind of designs with data only? Type of designs that we heard earlier, for instance, from Sinjig, where we have some exotic microreactors. Can we get them really only from data? Especially designs where choices of 0, 1, discrete choices are critical in the operation and may affect even how we handle uncertainty for the future, very, very importantly. Can causality be fully expressed through data only? Which is very important for decision-making, especially under uncertainty. And in general, how can we tackle decision-making problems under uncertainty with data only? All right, is that possible? So let me be a little bit more specific, the type of problems that I have in mind, all right? Because there are many, it's also a very fuzzy term, decision-making under uncertainty, and has many dimensions. So I'm going to go through a motivating thought experiment, okay, of the simplest possible problem, so as a benchmark of where we are and how the thinking can be further cultivated. And in that thought experiment, the way we define the two states, let's say stochastic programming, which is the easiest possible decision-making and uncertainty from a mathematical representation point of view, we distinguish two types of decisions. Here and now type of decisions, and these are decisions like design, so we build this house, for instance, or we build this type of reactors that Sinji talked about, here and now, right? Okay. And then we have wait and see type of decisions, which can be taken after the realization of the uncertainty. So the here and now are taken prior to the decision because there might be some time differentiators, if you wish, all right? And then in the presence of the here and now, we would like to make informed decisions about the future, and we have this degrees of freedom, which are the wait and see decisions in anticipation of the uncertainty. Okay, and this form of problems in different type of settings is very central to a great deal of application areas, very central to our process systems engineering and much, much beyond. Design and control is a class of problems like this, scheduling and control, design and schedule, all these kind of multi-scale type of decisions problems, but also in other areas like energy generation, distribution, project management, facility location, transportation, and so forth, all right? And I'm going to restrict even more myself, so that this is the, if you wish, the toy Pistikopoulion problem that we can think of in the terms of, so in the area of adjustable robust optimization, all right? So here, the setting of the problem is where, so you have uncertainty, U, X are the here and now decisions, Y are your wait and see decisions, and obviously you have constraints that are, interlinked all these variables as you move ahead. All right, so you'd like to, and the setting of the problem is that effectively you would like to check whether you can find X, so here and now decisions, so that for all possible realization of uncertainty in the future, there exists, if you wish, degrees of freedom, which is the wait and see variables that can anticipate and offset the effect of the uncertainty as we move, however, with the importance realization that the here and now design are taken prior to the realization of this uncertainty. Okay. And the way I'm going to approach this in this motivating thought experiment, I'm going to show to you as an example two model-based approaches and two data-driven approaches. We're not going to draw a very big conclusion, but it will be an interesting exercise, for discussions later during the drinking process, right? Okay. So for the model-based approach, one key approach that is very popular in the literature is you assume some linear decision rules. This is, you assume that Y, I remind you, are the wait and see decisions, those that are follow the uncertainty, or we intend to follow the uncertainty, that they have some functional relationship with the uncertainty itself. You postulate this. It's really an assumption, okay? So you set this here and now, the wait and see as a function, as a affine function, as a linear function, if you wish, of the uncertainty. And then the nice thing about this is that can be solved very easily as a robust optimization problem in a classical sense. The second approach that I'm presenting to you is something that I have never presented before, is that we have a way to generalize this, so we can deliver decision rules. This is some joint work we have been doing recently with the group of Professor Fenzi Yu. So we can get like expressions of the wait and see decisions, not surprisingly through multi-parametric programming, but this is not my main topic and focus today, as a function of the uncertainty and the here and now decision variable. Okay. And this is exact expressions for this class of problem. All right. I'm not going to bother you how we do this a lot. So these are two model-based techniques. And I'm going now to also pick two data-driven approaches, sophisticated data-driven problems, because this is a difficult type of problem. Perhaps I didn't quite show you the difficulty of this. This is, if you wish, a bi-level, actually it's a tri-level type of optimization problem, okay, if you want to pose it mathematically. Okay, so we're going to also apply surrogate modeling and optimization through a sophisticated tool. Okay, I picked here Argonaut from the group of the late Professor Pistikopoulos and subsequent developments, where you develop some type of surrogate models, all right? And then you apply derivative-based global optimization for the parameter estimation. So that's as good as it can be. And then machine learning type of via support vector machines, where effectively we try to get expressions of the wait and see variables as a functions of the first stage and the uncertainty, and we train, if you wish, through a kernel function in a supervised learning algorithm that will show you exactly what is the thought experiment here. So thought experiment 1 for the method 3, which is the, if you wish, the meta model and then fitting the parameters, is I'm comparing in a supervised one, where to generate the data, you effectively solve a static optimization problem. And the supervised, this is as good as it can be, where to generate data of effectively of the objective as a function of x, you solve a bi-level optimization problem, because you're trying to take into account what is the best options, the best, like playing chess, how best your opponent, which is you here, can do in the presence of uncertainty. Okay, so this is the two scenarios that I'm doing. And then for the machine learning algorithms, I also compare two sophisticated machine learning algorithms. In unsupervised, effectively, you are trying to get y as a function of x of u. So the unsupervised will be just blindly to use data, to give data for y and u. That will be the unsupervised version. So you solve a deterministic optimization problem as you move along. And the most sophisticated supervised machine learning experiment you can do for this will be to only give data for x, apply data of x, and solve a bi-level optimization, which will return to you y, u, and y, the optimal policies, and then you will do regression analysis from there on to get the expressions. So it's a very sophisticated, simple problem, but let's say we're looking as a benchmarking, how far can we go if we had the luxury to know the exact solution of the problem? And that's a fair question to ask, right? Okay. So, and here are my instances. It's as small as they get, but the complexity is in this bi-level optimization type of problem. So the first instance is a linear problem. This a small one. Okay, I'm not going to reveal the problems unless you want to see them. There's so, and I can provide to you all the details of everything I'm saying. Instance number 2 is a linear, but on top of that, in the here and now and in the here and now decisions, they involve 0, 1 variables. Okay. And in instance 3, we have nonlinear terms, and also they involve 0, 1 decisions in the wait and see, of course, in the here and now. Obviously, a more interesting will be if you have 0, 1 in the wait and see, but then all the data-driven approaches if I may postulate my argument, fail miserably. Okay, so let me show you first the exact, so here is I'm comparing the affine rules, which is an approximation to a problem. These are the exact solution, and you can see that the exact, obviously, this is the exact solution. The affine rules in the linear case, which is an exact approach due to duality, it's exactly, in instance number 2, which has 0, 1 variables, it approximates the solution, and it fails to instance 3 because it's not designed for this type of problems. All right, so this is now the results of the experiment we do with the, let's say, the gray, what people call gray box modeling, right? So you do a surrogate model, and then you fit parameters through global optimization. It's a sophisticated, if you wish, meta-modeling type of technique. And we do both the unsupervised and supervised. And here you can see that for linear problems, the unsupervised, as expected perhaps, they does not perform very well. Obviously for linear, supervised, not surprising, you get very close to the solution. But interestingly, for all other cases, either you are for or you fail. Okay, and I'm not saying this is, the best choice of algorithms you can do, but clearly, message number 1 is that these data-driven approaches, even though they have a lot of sophistication, they are not at the stage where they can handle this type of stage-wise decision-making, especially in the presence of novel type of design decisions represented through 0, 1 variables, for instance. Now, so a few remarks out of this is approximations such as affine rules, which are used very widely in the open literature, may be suboptimal. Affine rules cannot be derived for nonlinear problems. That's well known, okay? And data-driven techniques could arrive to near-optimal solutions only for continuous problems with sophisticated supervised data. We'll come back to this point. And they fail when we have mixed integer problems. Now, for the machine learning experiment, here are the results. I remind you exactly that this is it's a sophisticated setting of the problem, so it's a particular one where you are trying to get expressions of y as a function of x, the here and now, and u, which is the uncertainty. And you do unsupervised by simply supplying x and u data, and the supervised supplying x, and for this you solve a deterministic point-wise optimization, and supervised here is solution of bi-level optimization. So it's not data, random data, it's through the solution of bi-level optimization. So it's very bespoke type of data. And what I would like to draw your attention is when the experiment is unsupervised, it fails. That's not very surprising. When it is supervised, on the other hand, and through generating the right type of data through a bespoke bi-level optimization, then you get very good, if you wish, approximations of the solution. All right, so my 2 points here, just as a reference point through this thought experiment, is that using unsupervised data, we cannot really form the expressions we're after. Using supervised and very sophisticated with bespoke, if you wish, type of algorithms to guide the generation of the data, knowing a priori the solution mechanism, so to speak, we can generate expressions which are accurate enough. All right. So what have we learned from this, and what is more what we can learn in the future and where I think the field should go? All right. First of all, I'm not claiming at any moment that data are not important. They are very important, very useful, provided that we ask, as Professor Stephanopoulos taught us, the right type of questions. Are these the right type of data? Is the right amount of data? And are at the right timing? So do we collect data at the right timing? I would also argue, that we need as a community to come with some, if you wish, language that we all agree. So I think it's very misleading to go around and say model-free, variable-free, equation-free, derivative-free, all these terms which come from different communities because they don't represent the reality in the context of process systems engineering, because always you generate some type of model or meta model or super model with variables, perhaps projected at different type of spaces, it doesn't really matter, with equations, and you use primarily derivatives. In these data-driven approaches, derivatives is key. Okay, so I would like to diminish this myth. So within an algorithm, of course, not perhaps directly of the physical model we thought, but we need to work, okay. And I will argue that innovation in the type of product design, of the type of microreactor design that we are for, cannot really be obtained, or personally, I cannot see how it can be obtained only by data. You need knowledge, is essential, so therefore intelligent data is the key. In fact, guiding and generating bespoke data as if you know the algorithm that will give you to the solution, but that might be such a time-consuming that might beat the whole purpose of generating the data. You might go to high-fidelity models anyway. So just to summarize, in the interest of time and in the interest of having a drink as soon as possible, I just wanted to emphasize the importance of algorithms and obviously hypothesis testing and model development of the things we heard very nicely before. On the big data analytics, perhaps it's what I will call metaphorically modeling of the virtual reality. So we are mapping in spaces where effectively the effort of the model is in some virtual reality type of spaces. And then you train the algorithm to create the intelligence. So the emphasis of the model development is for the algorithmic development to reach your goal, if you wish. Whereas in model-based, if you wish, optimization, you try to model the reality itself, so to speak, and then you train the model, if you wish, through anything to create intelligent other through design of experiments, further to elucidate the model and so forth. And a side issue that we should always keep in mind is that optimization in some form or another is central to both, because one of the key that we do, especially data-driven, is parameter estimation. And this is central, it's a central optimization kind of problem. All right. And perhaps a hybrid approach of the things that we have heard earlier, where we combine models, the high-fidelity model development, we bring the data, we ask what type of data we need to generate as we move ahead, together with sophisticated algorithms, which might be either guiding the training of the algorithm or training the model itself, or both, could be the way forward. And I would like to, with this, to thank George for all the contributions, to wish him happy 70th birthday, happy retirement, and to thank, on behalf of the entire process systems engineering, for such an inspirational and intellectual leadership to all of us. Thank you, George.
Okay. Do we have a question for Stratos?
We all desperately need to go for a drink, I think, yes.
Okay, well, let's thank Stratos again for an excellent presentation.